First, let's examine the claim that 4 coordinates, 3 spatial and 1 temporal, are required to precisely describe events. This is the cornerstone of Einstein's theory of relativity, in which space and time are woven into a single continuum known as space-time. The revolutionary idea that time is relative, depending on the observer's speed and gravitational field, shattered the classical Newtonian concept of absolute time. This has been confirmed by experiments such as time dilation observed in particles moving at close to the speed of light and in clocks on fast-moving aircraft. Einstein's relativity proposes that time and space are not fixed backgrounds but dynamic entities affected by matter and energy. This simultaneous relativity, where 2 observers moving relative to each other may not agree on the timing of events, eliminates the concept of an absolute and universal time. The philosophical argument that time may be an illusion stems from this relativistic framework. If time varies between observers and is not absolute, some philosophers argue that it may be a construct of human perception rather than a fundamental aspect of the universe. This skepticism reflects the Cartesian doubt that questions the reliability of sensory information and the existence of an external reality. However, from a physical and scientific perspective, such philosophical considerations must be based on experimental evidence and mathematical formalism. The relativity of time does not deny its existence, but rather redefines its properties. The arrow of time, which always moves forward and never backward, is one such feature that requires explanation. The second law of thermodynamics, with its principle of increasing entropy, provides a macroscopic view of this arrow. Entropy, a measure of disorder, invariably increases in an isolated system, providing a thermodynamic direction for the flow of time. Quantum mechanics and general relativity also offer insights into the fundamental nature of time. In quantum mechanics, time is treated differently than spatial dimensions, leading to ongoing debates about the nature of time in quantum gravity. General relativity treats time as a dimension similar to space but distorted by gravity. When we move our investigations to the Planck scale, where quantum effects dominate, time can lose its traditional meaning. Other approaches to quantum gravity, such as loop quantum gravity and string theory, suggest that space-time itself may be emergent rather than fundamental. If space-time can emerge from more fundamental entities, what does this mean about the nature of time? Philosophy often teaches us to question the nature of our existence and the reality of our experiences. This skepticism extends to our sensory perceptions, as our senses can sometimes be deceptive. Descartes introduced the concept of cogito ergo sum, I think, therefore I am, to find a definite basis for knowledge. But even this leaves room for doubt about external reality and the interpretations of our sensory input. In contrast, scientific research relies on empirical evidence and the ability to measure, quantify, and observe phenomena. This approach is based on the scientific method, which provides a systematic way to test hypotheses and create a coherent understanding of the universe. Physicists rely on a set of strict criteria when considering the existence of any physical quantity. These criteria ensure that the entity in question is not merely a philosophical construct, but a tangible aspect of our universe. Can we measure the quantity? Time, despite its relative nature, is measurable. We use clocks to measure durations, and these measurements are consistent within their frames of reference. Can we assign a numerical value to time? Time can be measured in seconds, minutes, hours, and so on. These units allow us to precisely define temporal intervals. Can it be defined mathematically in a consistent way? Time is intricately woven into the fabric of space-time in Einstein's field equations. The mathematics of general relativity consistently includes time as a dimension. Is it observable, and are other observables inextricably dependent on it? The passage of time can be observed through the progression of events and the progression of countless physical phenomena, from the decay of radioactive material to the oscillations of pendulums. Many physical processes are time-dependent, which means that time is a necessary component of our physical theories. If these criteria are met, we consider the entity to exist in a physical sense. For example, in cosmological simulations, the evolution of structures such as galaxies and clusters over billions of years depends on the passage of time. These simulations highlight the role of time in the dynamics of the universe by showing how extremely dense regions grow due to the force of gravity. Given that time meets these criteria, it confirms its status as a quantity that exists within our physical reality. The concept of pathology in physics refers to scenarios where our current understanding yields absurd or inconsistent results. Examples of such pathological questions include: what happens at the central singularity of a black hole? Our current theories break down under these extreme conditions, leading to infinities and undefined behavior. What happens on length scales smaller than the Planck length? Here, space-time itself can lose its conventional meaning, and quantum gravitational effects can become dominant, leading to unknown behavior. How does a mass travel through space-time in a way that is distorted by its existence? The self-referential nature of this problem complicates its solution within current frameworks. These pathologies point to areas where our theories are incomplete or require new physics to solve. They serve as guideposts indicating where our understanding needs to be refined or expanded. The relative nature of time creates complications. According to special relativity, the amount of time that passes between two events depends on the observer's state of motion. For example, time dilation occurs when one observer moves at high speeds relative to another. Despite these relativistic effects, time can be measured and quantified, and is an integral part of the fabric of the laws of physics. The fact that time is relative does not make it pathological. Instead, it enriches our understanding by showing that time, like space, is part of a dynamic and intertwined continuum. Time can be measured and quantified, and is an integral part of the fabric of our universe. Pathologies in physics often point to the limits of our current understanding and the need for new theories, but time, as we measure and observe it, does not fall into this category. Continuing the discussion, let's now delve deeper into philosophical and scientific perspectives on reality and existence, focusing particularly on the measurement and conceptual understanding of time and other fundamental aspects of the universe. While time always moves forward and never backward, the arrow of time, its one-way flow, is not fully understood. Thermodynamics explains the second law, which states that entropy in an isolated system tends to increase, giving a direction to the flow of time. However, this thermodynamic arrow of time does not fully explain why time appears to move in one direction at the macroscopic level. At first glance, time might seem pathological because of its relative nature. The fact that time measurements depend on the observer's state of motion might seem to undermine its consistency. Consider the classic thought experiment involving a person on a moving train and a stationary observer on a platform. An observer on a moving train measures the time it takes for a light wave to travel from one end of the train to the other. For this observer, the time it takes depends on the distance the light travels and the speed of light. A stationary observer on the platform measures the time it takes for light to travel the same distance on the train. However, because of the motion of the train, this observer sees the light travel a longer distance. As a result, the stationary observer measures a longer time interval for the light to reach the end of the train. In addition, the stationary observer perceives that the person on the train, along with everything else on the train, is aging more slowly. This time dilation effect occurs because, in special relativity, time appears to slow down for a moving object compared to a stationary observer. Is this paradoxical or pathological? Not. The relative nature of time is a consistent and predictable phenomenon within special relativity. When the train stops and both observers compare their watches, they will see that their measurements of elapsed time are different. However, these differences are consistent with the predictions of relativity. Each observer can accurately predict the other's watch readings, demonstrating the internal consistency of the theory. The fact that time is relative does not mean that time does not exist. On the contrary, It emphasizes the dynamic and interconnected nature of space and time. The relativistic effects of time dilation and length contraction are experimental realities that have been confirmed by numerous experiments, including high-speed particles and precise atomic clocks. Investigating whether time is merely a perceptual construct leads us to consider symmetries in physics. Many laws of physics exhibit time symmetry, meaning they are invariant under time reversal. This symmetry shows that the fundamental equations that govern physical processes do not naturally distinguish between the past and the future. Consider the motion of a ball under gravity. Whether the ball is falling under the pull of gravity or rising against it after being thrown, the underlying physics remains unchanged. This time-symmetric nature of the laws does not provide a clear distinction between the forward and backward flow of time at a fundamental level. As a result, the relative nature of time is a well-known, if counterintuitive, aspect of our universe. While the time symmetry of the laws of physics challenges our intuitive perception of time's arrow, it does not mean that time is an illusion. Instead, it points to deeper, not yet fully understood aspects of the nature of time. Many laws of physics, including those governing motion, gravity, electromagnetism, and the strong nuclear force, exhibit time reversibility. For example, Newton's laws of motion and Maxwell's equations of electromagnetism do not inherently favor a time direction. Observing a system governed by these laws does not provide an inherent indication of whether time is moving forward or backward. However, there are fundamental phenomena that break this symmetry and reveal the one-way flow of time. The weak nuclear force, which is responsible for certain types of radioactive decay, exhibits a particular time asymmetry. Consider the process of beta decay in a heavy atomic nucleus with an excess of neutrons. In this process, a neutron decays into a proton, an electron, and an anti-electron neutrino. This decay is natural and spontaneous. However, the reverse process, in which a proton, an electron, and an anti-electron neutrino combine to form a neutron, does not occur spontaneously in nature. This asymmetry is a feature of the weak interaction and serves as a clear example of a time asymmetric reaction in physics. The second way to distinguish between forward and backward progression in time is through the concept of entropy and the thermodynamic arrow of time. Often misunderstood as a measure of disorder, entropy represents the number of possible microscopic configurations that correspond to the macroscopic state of a system. When you beat an egg, the initially separated components, yolk and white, mix, increasing the entropy of the system. The energy gradients and potential energy barriers that maintain separation are overcome, leading to a thermodynamically more probable state. Dropping a glass and watching it shatter involves releasing stored potential energy. The broken pieces represent a higher entropy state than the intact glass, because there are many more ways to organize the pieces than there are to keep the glass whole. Consider a hot room and a cold room separated by a divider. Each room is internally in thermal equilibrium, meaning there is no energy gradient between them. When the divider is removed, particles from the hot room and the cold room begin to mix. Heat flows from the hotter region to the colder region, increasing the overall entropy of the system. The process continues until a new equilibrium is reached, where the temperature is uniform throughout the combined space. Removing the separator results in an increase in entropy, which shows the thermodynamic arrow of time. This process is irreversible. When the rooms reach thermal equilibrium, they do not spontaneously return to their original separate hot and cold states. Initially, the system can do work because energy gradients are present, but once equilibrium is reached, no more energy can be extracted. This state of maximum entropy represents a system that can no longer do work because all energy differences have been equalized. While most fundamental laws of physics are reversible concerning time, the weak nuclear force and thermodynamic processes provide clear examples of asymmetric behavior for time. The increase in entropy dictated by the second law of thermodynamics allows certain processes to proceed in only one direction, providing a macroscopic arrow of time that is compatible with our everyday experience. Despite philosophical and scientific debates, the physical reality of time is beyond doubt. It is an essential component of the universe. The boundary between events with definite consequences and those that have not yet occurred is one way of defining the present moment, or now. As described by Lee Smolin, this transition from uncertain to definite states emphasizes the perceived flow of time. In quantum mechanics, this transition marks the point at which quantum probabilities become classical realities and determine the present. As a result, while the fundamental nature of time and the exact reason for its one-way flow are still being investigated, its reality as a measurable, observable, and quantifiable entity has been firmly established. As our understanding of the universe deepens, we may discover more about the relationship between time, entropy, and the fundamental laws of physics. Thanks for listening, and take care.